Hello, and welcome to another episode of Risky Business. Uh, my webcam is in a different position right now because uh, I'm experimenting with Google Hangouts, and this webcam position looks better on Google Hangouts, in my opinion. Um, so I've been really busy with work, and there's also some exciting content coming down the pipeline for Risky Business this week, which is why March 17th is to be decided on regarding the date of the stream, or the time, I mean. And that's also why I'm messing with Google Hangouts. So uh, I'll leave it as a bit of a surprise. If you're following the series closely, you might already know the reason and what's going to be coming, but for now, I'll just leave it as a bit of a surprise and say that the schedule this week is kind of up in the air. Not that I stick to a schedule very well anyway, but um, last time on Risky Business, we looked at understanding the relationship between the PLIC, the MIE register, and the MIE bit in the mstatus register. And at the end of that, I had a question, and I posted that on the SiFive Forums, and we got an answer from Megan Wachs, who I believe is an engineer at SiFive. I think she is responsible for pretty much all the code we've looked at. I think she wrote all of that. I could be wrong though, so don't quote me on that. But she responded to my question and says those lines of code, and the lines of code are these lines right here at the start of reset demo. It clears the MEIE and MTIE bits in the MIE register, and I was wondering why you wouldn't just clear the MIE bit in the mstatus register instead. And so I asked this question, and she says those lines of code don't make a lot of sense anymore. They are left over from an earlier version of the code, which allowed reset demo to be called from other functions. They simplified the demo before they released it, and the same could be achieved by just disabling interrupts globally. There is no special desire to keep the MSIP interrupt enabled. We just know in this demo we never enabled it. So the answer to our question is that we really don't need to be messing with disabling the interrupts at all in this demo, and that at one point it was something that was perhaps necessary, and they just happened to know that the MSIE didn't need to be cleared in the MIE CSR, so they just happened to do it this way instead of using mstatus. So I don't really know why reset demo being able to be called from other functions would have anything to do with needing to disable the interrupts. We might actually learn kind of the reason behind that as we study the interrupts more. Because we haven't really gotten into like the actual interrupt sources and seen real world use cases of the interrupts yet. We've just really been diving deep into the implementation of how interrupts work on the machine, but we haven't really taken a practical look at how interrupts, like what they can actually be used for, right? But we definitely will get to that at some point. And the other thing, let me give this a like since she answered our question. And the other thing is I updated the Freedom E SDK to the latest version. It might be behind now, but I updated to 3A0 1AC1 over the weekend. I also stashed my changes. So right now we are just on the vanilla Freedom E SDK without any changes to the demo programs. And so you can see the files that changed here. So there were some changes to the demo GPIO. They refactored out the PLIC driver to be a common thing. It's under BSP drivers PLIC. And I looked at the diffs of demo GPIO before I did this update. So there were some other things that changed as well. You can see here that demo GPIO.c has been changed around a little bit. And I guess the Makefile has been changed as well. And I think those are pretty much the only real things that matter to us. Like here again, you can see that the PLIC driver was refactored out. But yeah, that's the main thing that affects us. So let's open up the code again. So I'm going to go to the demo GPIO directory. And we'll take a look at the Makefile as well as the demo GPIO. So the Makefile specifies the BSP base. We're compiling with O2, no built-in printf, use PLIC, use mtime. Target is demo GPIO. The C sources are demo GPIO.c. And then you can see here it's pulling in the PLIC drivers from the BSP base instead of being local to the project. And there's also a common.mk. Maybe we should take a look at that. I don't think we looked at the Makefile last time. Like, I don't think we ever looked at the Makefile for the demo GPIO program until now. But anyway, here's the program. You can see that one thing that's changed is we used to calculate a bunch of pointers up here to like different GPIO addresses. And now we're using these macros, the GPIO reg. So you can see that this is just giving you a pointer, and they're doing it that way instead of having a bunch of pointers defined up here. So let me see if I can go to the Freedom E SDK on GitHub. And GitHub has, on the web interface, it has a pretty nice diff capability. I mean, we could do the diff locally too, but I like the web interface's diff output. So if we go over to software, demo GPIO, and then we hit history. So I want to see the diffs since the one we were on. So we were somewhere around here. So here's where they added the PLIC driver.h. So we had that, so we were at least on this commit. Let's check a few more of these. So yeah, we had this commit as well. And then it looks like this commit just did white space. So it's the commit after that one where things start changing from what we were looking at. So let's take a look at some of these. So this change right here doesn't affect us necessarily directly, I think. But you can see here what happened in this change is they refactored stuff relating to the libc implementation. And that's going to be interesting to us in the future because, like, right here we can see under bsp librap sys write.c we have an implementation of write, which is what we call in the demo to do printing to the console. And you can see in here it's using the UART stuff, which we already knew it would be. So we're definitely going to be taking a look at that at some point. And it looks like there's a lot of interesting stuff in this commit that you could take a closer look at. Here we see the common.mk. So it looks like that's a Makefile that's common to everything. So we probably won't take a look at that right now, but at some point we should remember to take a look at that. So this change right here, use register macros instead of volatile addresses, that's what I was talking about having changed. We used to have this code right here, right? We had, and you saw this on the series in the previous episodes, where we had G output vals and input vals and output en, pull up en, input en. And we didn't get around to looking into the GPIO stuff, but I believe it's on the to-do list. So if I fire up Milton here, you can see I have GPIO stuff on the to-do list to look into. And so you can see an example of stuff that changed here. So like here they're referring to G output vals, and now you can see they're doing the same thing, but they have a macro instead. So they use that GPIO reg macro, and they pass it GPIO output val. And that returns, I guess, a dereferenced pointer to that location in memory. And again, you can see how they are just replacing dereferenced pointers with that stuff. So I think that was the main change that happened in our program. They also added atomic bit banging to the demo. So they included std atomic.h, And it says here pin 19 of the Hi5 1 or A5 on the RD dev kit is being bit banged for a GPIO speed demonstration. So you can see here, here's another GPIO thing, and they're doing something with it there that we will research at some point. And then in the while one loop, you can see that it does an atomic fetch and exclusive OR with this GPIO output val and a mask. And then there's also a comment that says, demonstrate fast GPIO bit banging. One can bang it faster than this if you know the entire output val that you want to write, but atomics give a quick way to control a single bit. So we don't know anything about like the GPIO stuff yet, or what they really mean by bit banging. I assume bit banging refers to just like pushing stuff over the pin as fast as possible. But we will definitely learn more about that at some point. So what else has changed? Okay, so they changed that demo of the bit banging up to use atomic fetch exclusive OR explicit, and then they also passed memory order relaxed. So that says it avoids unnecessary fences. And yeah, also you can see that all these commits are by Wachs5, which would be Megan Wachs, who I mentioned as being the one who responded to us on the forums. So that's why I think she wrote all this code. I assume she's not just committing code that other people wrote. I don't know. I know she's an engineer because she did an interview, so I'm pretty sure she wrote the code. So shout outs to her. And then we have move PLIC driver code to a common location. That's the other thing I mentioned we saw in the changes. And you can see it here that instead of including PLIC driver.h, they include PLIC/PLIC driver.h. There's also a change to the includes in the common.mk, and a change to C sources in the Makefile. And then the same change to the include in demo gpio.c. So this one was in the PLIC driver.c that one changed. But yeah, that covers all the changes to the code we've been looking at. So for the most part, everything is still the same. And we were looking at reset demo. So we looked at this part of the code right here, and that's what the question was about. We understand what this does. We looked at that. It's just an array. We looked at print instructions, which is like the actual program. For the most part, that's what does the printing to the console. But we haven't dived in deep to really fully understand everything that happens in there, which is on the to-do list. We also looked at the PLIC in depth earlier, so we already know what PLIC enable interrupt does. and we know what set priority does, so we understand all this stuff. And then we also have this GPIO stuff that's on the to-do list to look into. And then finally, at the end of it, you can see we re-enable this stuff. And again, it probably isn't, like, all of this stuff right here probably is not necessary in this demo, based on what Megan said. But it's in there nonetheless, and we understand what all of it does. So the next thing to look at is the Carplex local interrupts. So I believe we will start on that today. If we didn't start on it already. We probably already did start on it, didn't we? So let me reload these documents here. Okay, so which one were we looking at last time? I believe we were looking at the E3 Carplex manual, Chapter 6, Carplex local interrupts. So I believe we read 6.1, and we took a look at this table here. So I'm just skimming over it right now to get a little bit of a refresher. Okay, and then 6.2, MSIP registers. Machine mode software interrupts are generated by writing to per hardware thread memory mapped control register. We might have already read this. The MSIP registers are 32-bit wide WARL registers where the LSB is reflected in the MSIP bit of the associated hardware thread's MIP register. Other bits in the MSIP registers are hardwired to 0. The mapping supports up to 4095 machine mode hardware threads. So the MSIP registers are 32 bits wide, and the least significant bit is reflected in the MSIP bit of the associated hardware thread's MIP register. So does that mean that MIP and MIE and all those registers are per hardware thread? Meaning there'd be a separate MIP and MIE register per hardware thread? I was thinking it was global. Because like the CSR instructions don't specify, you don't pass it like the hardware thread, but I guess maybe it would know that regardless. So it might be able to refer to the specific register you want using those instructions, even though it's different depending on what hardware thread you're on. I'm not totally sure. So like mstatus, I know that the PLIC is per hardware thread. And then I was thinking mstatus is global. But I guess I could understand MIE and MIP being per thread. I want to take a look again. Does this say anything about it being per hardware thread? I mean, from what I'm skimming over in this document, we've read it all on stream, but whoops, didn't mean to do that. Okay, so from what I'm reading and from what we've already read, this one kind of suggests to me that it's global. But there is something about hardware thread here. Interrupts are considered to be globally enabled if the hardware thread's current privilege mode so it does have to be per thread, doesn't it? Because the registers are named based on if it's machine, hypervisor, supervisor, or user mode. And those privilege modes are per thread, I believe, per hardware thread. So maybe these things are per hardware thread. That might be a question to ask on the forums. I don't know if I'll post a topic about that, but for now, let's just keep in mind that that might be the case. I'm sure we'll figure it out at some point. So let's go back to reading documentation here. So LSB is reflected in the MSIP bit of the associated hardware threads MIP register. Timer registers. Machine mode timer interrupts are generated by a real-time counter and a per hardware thread comparator. The mtime register is a 64-bit read-only register that contains the current value of the real-time counter. Each mtime compare register holds its hardware thread's time comparator. A timer interrupt is pending whenever mtime is greater than or equal to the value in the hardware thread's mtime compare register. The timer interrupt is reflected in the MTIP bit of the associated hardware thread's MIP register. So here you see the different MSIPs for each different hardware thread. And so, I mean, there's 4095 total, right? 0 to 4094. That's 4095 total different hardware threads, and it says that's how many hardware threads are supported. And so what it's telling me is that for every hardware thread, there is this MSIP register, which is 32 bits. You can see in the address it's a difference of 4 bytes. And these 32-bit registers, there's 4095 of them. And then the least significant bit in each register is supposed to correspond to a bit in the MIP register for that particular hardware thread. And there is a similar bit for the timer. So the way that works, MIP has to be per thread. So there's 4095 different MIP registers then to correspond with the 4095 hardware threads. And presumably the same for MIE then as well. So I do want to go back again. I'm still curious. I'm pretty sure MIP and MIE are per hardware thread now, but now I'm wondering about mstatus. Is mstatus per hardware thread too? So maybe there's not a way to say that we want to disable all interrupts across all the different threads. It might have to be per thread, is what I'm beginning to think now. So all of this stuff is talking about mstatus, but not the part we care about. Okay, machine status register. The mstatus register keeps track of and controls the hardware thread's current operating state. So that is per hardware thread as well. So all of these registers are per hardware thread. I guess the only like global registers would be the general purpose registers. If I'm understanding that correctly. So let's continue reading. That is it. So we read all of chapter 6. I guess it was a pretty short chapter. So that is everything they have to say about Carplex local interrupts for the E3 Carplex manual. So let's take a look at the E300 manual. So does this have anything about the Carplex local interrupts? I'm not seeing anything about the Carplex local interrupt controllers so far. I don't even see it on this diagram here. So the E300 platform is the first member of the Freedom Everywhere family. By combining a highly configurable base platform with customer-specific hardware extensions, Freedom Everywhere family provides low NRE and rapid time to market solutions for performance, cost, and power-sensitive embedded and Internet of Things markets. Each E300 system on a chip includes a SiFive E3, risc-v Carplex with integrated instruction and data memories, a PLIC, on-chip debug unit, and an extensive selection of peripheral devices. This manual should be read with the E3 Carplex manual. All aspects of the base E300 platform can be flexibly configured. In addition, the platform can be readily extended with customer-specific instruction set extensions, custom coprocessors, custom accelerators, custom I/O, custom always-on blocks. The resulting application-specific E300 system on a chip is optimized for manufacture in a TSMC 180 nanometer process. Okay, so the fab they use for this is TSMC 180 nanometer. So if you're interested in fab stuff like that, presentation I showed you, Indistinguishable From Magic, if you like that kind of thing and want to know more about the fab process that SiFive uses, take a look at TSMC 180 nanometer. I'll probably look that up myself off stream and see if there's any fun information about that. But that didn't answer my question. So, where were we? We were at GPIO when we looked at this document, and we scrolled up all the way to the beginning. So there wasn't anything about the Carplex local interrupts in any of that. So let's just take a look at the table of contents here. There's stuff about the UART, SPI, one-time programmable memory, pulse width modulation, but none of that covers Carplex local interrupts. So the FE310G000, which is the actual specific chip that we have, does. So you can see in this diagram, we do have Carplex local interrupt controller. And you can see it says here the Carplex local interrupt controller supports the standard timer and software interrupts. Does this document have anything else about Carplex interrupt controller? It's not looking like it. So I think we've read all of the documentation that covers Carplex local interrupt controller. So presumably it didn't really go deep into how the Carplex interrupt controller functions. Presumably it is similar to the PLIC, if not the same. And it's only used for the local interrupt sources that are standard. And we saw that briefly in the documents about the PLIC in the risc-v spec, the privileged spec. So if I go back here, and find the part on the PLIC, this must be the wrong document. This looks like the user level spec. Yes, it is. Here's the privilege spec. So we're going to jump to wherever the PLIC stuff is. Local interrupt sources. So I am looking for the standard local interrupt sources. So where do we have information? I know I saw it at one point when we were reading this documentation, that it talked a little bit about some standard local interrupts. But where did I see that is the question of the day. It might have been in the PLIC overview. I don't think so, though. So I wonder where those are defined. It might have been in the stuff about the CSRs, actually. So let's take a look at MIP and MIE again. I think it's the bits in here that are referring to local interrupts. So like MTIP, for example, the timer interrupt. If I'm understanding correctly, that's a local interrupt. And I imagine the other ones, like the software interrupts and the external interrupt, I think the CSR is the mechanism by which we are messing with local interrupts, maybe? Can I like search this document for a local? Maybe I'm thinking of mstatus. Wait a minute. Each hardware thread has a number of local interrupt sources that do not pass through the PLIC, including the standard software interrupts and timer interrupts for each privilege level. So that says there's standard software interrupts and timer interrupts. So is that what we're thinking of? There's also additional non-standard local interrupt sources that can be made visible. So that would be if there's like platform dependent local interrupt sources. And according to the documentation we just read on the the actual chip, we only support the standard ones on this chip. Okay, so let's look at mstatus one more time. From what I understand, there's two different standard local interrupts, and that's the software interrupt and the timer interrupt. So if we go to mstatus, and I want to look at the layout of the register. Okay, here we go. So the MIE bit, this bit right here would be for the machine interrupts that are global. And then where's the timer one? Does this not have one for the timer? Or the software? So I guess those are the in the MIE and MIP registers, not the mstatus perhaps. Because I don't see timer and software in this register. So yeah, I think that's all there is to say about that. So I think that covers everything related to Carplex local interrupts. So let's see if we can understand this code then. So this says it sets the machine timer to go off in 3 seconds. There is mtime and mtime compare, and we calculate those addresses. Did we see where those addresses were? We might have. I remember there was a diagram that we looked at. This one right here. Okay, yeah. So this tells us the addresses that we need to go to. So it's per hardware thread. And there's this mtime compare register, and there's also this mtime register, which is at 0x0200BFF8. There's only one of those. So you can see here we're getting mtime and mtime compare. Interestingly, we're doing the mtime computation as CLINT base address plus CLINT mtime, which makes sense. The base address must be 0x02000000. And then mtime compare, we're doing that base address again, plus CLINT mtime compare. What I'm surprised about is that there's not a shift by the mhard ID, or the hardware thread ID, right? Like normally what you'd expect to see is we do that instruction to get the hardware thread ID, and then we shift in order to get the correct one of these. Because like that's how we compute an address in the PLIC driver, right? So, I mean, these are per hardware thread. So what is CLINT mtime compare expanding to? So that is what we need to research next. Let's go back here, and we want to go to the BSP, and I wonder, doesn't look like we have it, so in the history of my terminal. So I need to find the appropriate files. So drivers, PLIC, PLIC driver.h, drivers, PLIC, PLIC driver.c. What else do we use? What's under include? See if there's anything in there we care about. There's a CLINT.h in there. That looks relevant. What else? Environment. Encoding.h. What else is there? SiFive1.h. Sure. Environment. Freedom E300 SiFive1. init.c. Environment, Freedom E300 SiFive1, platform.h. So here's a bunch of files. So let's search for CLINT. Okay, here's the various values. So mtime compare is 0x4000. It does have the mtime compare sized. It says the size is 0x8. There's mtime, and there's mtime size. Regarding the sizes, those should be amounts to shift by. I guess I need to do the math to know why it's 8. That's probably something we'll do on stream at some point, because we're not doing the shifts here, but the shifts should be moving us by multiples of 4, because it's 4 bytes between registers, because they're 32-bit registers. Memory mapped registers, that is. And then, so mtime is 0xBFF8. Where is the one that says the base address, though? So here we can see some code that's using the Carplex local interrupt base address. This is the init.c in environment Freedom E300 -1. But let's move on from there. Okay, here it is in platform.h. So it defines the CLINT base address to be that 0x02000 and a bunch more zeros, right? So that is the address that we thought it was. We also saw the BFF8 for mtime, which is the address we thought it was. And was mtime compare 4000? It should be 4000. So or not that file. Let's see, which file was that in? The CLINT one, right? Okay, so yeah, you can see it's 4000. Now, the thing that's interesting about that is we're hard coding that we're on hardware thread 0. So that's pretty interesting to me that we hard code that we're on hardware thread 0 right here. I think a more proper way to write this code would be to do the instruction that gives you the current hardware thread ID, and then use that and do some shifting to compute the proper address for whatever hardware thread you're on, because this code will break if you're not on that hardware thread. Or I mean, it doesn't necessarily break, it just does what you don't expect. It's going to set the value for a different hardware thread than you're on. If you're not on hardware thread 0. So just to review what I'm talking about here, if we go back to the PLIC driver, you can see the common thing to do is you get the hardware thread ID using read CSR mhart ID, and then you see they've got the base address, and then they move by the offset, which gives you the start of the PLIC enables. And then the PLIC enables move by some amount. And to get the correct one, what you do is you take the hardware thread ID and then you shift by the shift per target, right? So the size values that we see should be a value that indicates the amount you shift by target. And then you do like, let me go back to the CLINT stuff. So you would do the CLINT base address, and then you would add CLINT mtime compare, and then you would add the hardware thread ID shifted by like mtime compare size, which should be the amount such that it will move you 4 at a time, right? That's what we expect the code to do. I don't know if that's the correct value, the mtime compare size, because like I say, I would need to work that out on the whiteboard, which is something I think we should do. But I don't think there's time for that today. In fact, we are out of time for today. But yeah, it's just interesting to me that we're our code here is kind of brittle in that it assumes hardware thread 0, which is fine, I guess, if you're not doing any multi-threading, which this program doesn't. So we just know that our program doesn't do any multi-threading, so we just use hardware thread 0 without actually checking if that's true, because we know it will be, because it's the only thread that's running. right? But I don't think that's a good practice necessarily. Like if you're doing hardcore optimization and you know for a fact that you're going to be running on a certain thread, then you can squeak out a little performance doing something like this, which isn't very safe, but you know, well, I know it's going to be this hardware thread, so rather than actually doing a machine instruction to check it, which is going to take time, I can just assume the correct value. And if you can guess correctly, and it will always be reproducible, such as this case here where it's the only hardware thread and you know it's always going to be 0, then that can actually save you a little bit of performance. So I can see why you would do it from a performance perspective. But in terms of just writing general code, I don't think that's necessarily a good practice. So that's my opinion on that. And we will dive into changing this code. We might not actually change the code, but we will dive into seeing how you would properly write it to pick the mtime compare based on your hardware thread. And the other thing I should mention before we quit today is that I guess I have this up now, but I should mention I did try to compile the Freedom E SDK. I pulled in these new changes, right? But I tried to compile it and it failed to compile. I'm pretty sure the reason it failed to compile is if we go to the SiFive Forums and we go to Hi5 1, Arch Linux and the Hi5 1, I just pulled the changes. I'm not using the package that I'm technically a co-maintainer of, but I don't really do anything on it, the one that I should, but I don't. This nonerkao guy, shout outs to him. He is the main maintainer of that package and is doing all the work on it, even though I'm technically a co-maintainer. And I believe he has talked about this in this thread. So you can see here is someone, for someone it failed to compile, and I believe this is the same error that I got when I tried to compile it last weekend. And it's an issue with the latest Flex, according to Ashley Towns. And if you used an older version of Flex, it'll build fine. And in the package, it does require the proper Flex version, I believe. But like I say, I'm not using the package. I already had the Freedom E SDK downloaded before there was a package, right? So I just went in that directory and did a pull to pull in the latest changes, because why not, right? I already have it, so. But as a result, I also did system updates, of course, and I now have a newer version of Flex. And that would be what caused me to fail to compile it properly. So if I downgrade Flex, that would fix that issue, I believe. But I'm not going to do that for a while. I'll do it when we need to actually compile stuff. But right now we're just studying code, so, it doesn't really matter for me. But yeah, I believe that's everything for today. So thank you everyone who tuned in today. And thank you everyone who watches on the YouTube archive at risky.tv. And you can follow me at hmn_risky to get updates about the series. This would be a pretty good week to do it because, like I say, I don't always follow the schedule as closely as I should, but I do try to tweet when the schedule changes. And this week particularly, I don't even know when exactly I'll be streaming on Friday, because depending on how things go, we might do a live stream at like 1:30 CDT PM, so 13:30, and If that doesn't work out, there's a lot of technical stuff I need to figure out right now. And depending on how that goes, I might not do a live stream then, but I might be recording something that's going to go on the channel later. And if that's the case, I'll probably stream at like 2300 CDT. It's CDT instead of CST now because daylight savings or whatever, you know. But we'll see. We don't know the schedule for Friday yet. So if you want to know, also Hossein got his t-shirt. Shout outs to him. So yeah, that's everything. If you want to follow the stream and watch live, you should probably follow the Twitter to know when I stream. And yeah, thank you for tuning in. I will see you next time. And stay risky, everyone.